Okay, so today's midterm review. So basically, this can be driven entirely by your questions, or I've got kind of a few slides that show maybe jog memories and maybe generate some of those questions. Then next lecture period. So today's Thursday, so it'd be Tuesday of next week. We'll have stage one. Now that it's a Canvas-based exam, it will become available Monday at midnight. So you'll actually have 72 hours. You can start the exam, or I guess finish the exam. So it's going to be available Monday, Tuesday, and Wednesday until 11:59 p.m. So all three of those days. It's a 90-minute exam, so it's a timed exam. It's individual, closed book, closed notes, but you get two double-sided formula sheets that are self-produced. So I don't want any photocopies or screenshots included on there, but you can type it, that's fine. It's taken via Canvas with lockdown browser. Again, it's 90 minutes. You can start it anytime within that 72-hour window. It has to be finished before that 72-hour window ends. So if you want to take it on Monday, that's fine. You can just sort of, skip coming to class. If you'd like to come to class and take it in this room with me proctoring, that's fine. You could come in here and then start the process. You still have to take it with a laptop, with Respondus, and go through all of that. And so in fact, once you sit down here, you don't have to wait for me to arrive. You can start it whenever you're comfortable with starting it. But instead of giving you the full 90 minutes, it's designed to be a 75-minute test, which means to me, like, I think most people will finish it in 30 to 40 minutes. And so there'll be a plus or minus, and some people will extend out, but very few people will need the full 75 minutes. I added 15 minutes just for technical issues having to do with Respondus. So if you feel comfortable to take it in the classroom and are okay with limiting yourself to 75 minutes, that's fine. You can come here Tuesday and take it. Otherwise, take it wherever you would like to take it, wherever you're comfortable. But just keep in mind, it's an individual exam, closed book, closed notes, two double-sided formula sheets. Then a week from today, so that will conclude. You won't see your scores. You won't see any answers. But then what will open up Thursday at midnight, so you have all day Thursday, all day Friday, and all day Saturday, is the exact same test as stage two. But then it's open book, open notes, open Canvas. You can collaborate with other students as long as they're in the class. You can submit it multiple times, and we'll take your latest submission. Yes, I guess that's kind of the key points there. So the collaboration options, it can be in person, it can be digital. If you want to set up your own Discord channel for it, that's totally fine. If you want to use our Slack that's been set up for you, that's fine. Canvas discussion boards, whatever you'd like. There's a bunch of different options that you can do to collaborate here. But again, it's the exact same exam as up here. So one of the things that I actually prompt you to do at the end of stage one is maybe on, I didn't mention it here, but you can also have blank sheets of paper. And so if you've got blank sheets of paper that you're using for notes, you have to show all the paper to the camera to show that they're truly blank. Then before submitting your stage one, you could record your answers so that you remember what you put down for each question. And then you can revisit the ones that maybe were particularly problematic and check with your peers, or just check with your notes and things like that. And then you can take it during stage two. So then Saturday night, stage two will close. And then sometime after that, I'll release the solution sets, which will be the same solution set for stage one and stage two. So you can review your scores and everything. And your total midterm score, which is, I think, 20% of your grade, will be 80% this score plus 20% of this score. And so that's kind of what I summarized here. So any questions about this multi-stage setup here? So this is timed and individual. This is untimed, but you've got a 3-day availability window to get this one done. You've also got a 3-day availability window to get this one done. The exam's designed to be completed in no longer than 75 minutes, but I give you 90. Most people are probably going to take about 40 minutes to complete it, some less, some more. Question? That's right. Yeah, this will not be on lockdown. This is the only one on lockdown. And I'll check for questions online here in just a second. The other thing that I didn't mention here is a small fraction of your midterm grade is that lockdown browser compliance test that I sent. If you hadn't completed it, I sent you a reminder, I think yesterday, about it. And you'll need to complete that to unlock the midterm module, which has a bunch of resources in it, plus these things here. So that's kind of other thing there. So let me check, see if there's any questions online. I see, will the exam be purely free response? Will be multiple choice questions. This is an auto-graded exam. So I use a number of different tricks with that. So I might have calculation questions. I'll bring this up in a second. I might have multiple choice questions. I might have fill in the blank questions, or multiple fill in the blanks, matching questions I like a lot. I like select all questions. So it looks kind of like multiple choice, but you can have multiple answers or no answers. So, and then calculation questions. I might ask you to sort of do a chi-squared, but I could ask you for the answer to the chi-squared, like, put in the chi-squared value that you calculated. Or I might give you an expression that you'll need to calculate the chi-squared and ask you to fill in one of the missing variables in the expression. So there's ways in which you'll end up having to do sort of long form design or analysis, but you're going to answer the questions in a way that Canvas can very quickly grade. So it's all auto graded. It's so think Canvas style or Scantron style. So it's not free response. And so at the end of stage 2, when I put the release the solution sets, you'll get your scores. So you'll get your scores within a day or two after you finish stage 2. So hopefully that answers that question. Any other questions about, yeah. There will be in some questions. So if I've got so there are certain question styles that Canvas does apply partial credit to. So if it's a multiple choice, you can select multiple. If you select a fraction of the multiple, you can get partial credit for that. So there's that. And as I'll mention, I don't know if it's on the next one, no, it's not yet, but basically all of the questions, regardless of how long it takes you to do them, are going to be 1 point. And so I never quite understood why faculty give like 30 points for a chi-squared and 1 point for a conceptual question, because when you go to a job interview, no one's going to ask you to do a chi-squared. And no one will ask you to do a chi-squared in the job, right? Because there's tools for that. But if you don't know what a chi-squared is, you won't get the job. So to me, it's just as important for you to know how to do a chi-squared test as it is for you to know what type of test the chi-squared test is. And so, so when we think about partial credit, a lot of times I think when students ask me that question, they're saying, oh, in order for me to do this, I need to go through like 10 different steps. There's a bunch of arithmetic, I could miss something. And so can I get partial credit for like, this will be a 15-point question. I'll get 5 points for doing the first part and another 5 for this part or whatever. And I kind of normalize that by making everything worth a point. Now, in some cases where things do really have stages, like your latest homework, you have to, maybe you have to derive a CDF from a PDF. You got to invert the CDF, and then you got to draw numbers from it. Well, those are like 3 discrete stages, and I wouldn't want you to mess up on one and have downstream issues. So for that sort of problem, I will probably break up into 3 individual problems. So although on a paper exam, I might give you all 3 together and then give you partial credit, on this type of exam, I'll give you them separately, so that if you happen to not, if you happen to have a small arithmetic mistake in the first one, you sort of effectively get to reset, because I will change the conditions going into the second one so that no errors you have in the first one will carry over. So I don't have partial credit formally, but the exam is designed so that the credit is sort of divvied out among the questions as if there was partial credit, if that makes sense. I think there's a question up here as well. Did you raise your hand when he earlier? Okay, go ahead. Yeah. Yeah, so stage 1, you can take Monday, Tuesday, or Wednesday, whenever you'd like. So if you want to come here and take it, that's fine. If you want to take it elsewhere, you can take it during this time, but not in this room. That's fine too. Yeah, I mean that if you think that will help, then yeah, absolutely. You can use other. The only thing what I want to exclude you from using is like Google. Like if you know, so I want you to sort of base it off of things you've learned how to do in this class. And so there's a little bit of an honor system here, but I'm sort of saying that the acceptable tools to use are tools that you would typically use to do classroom assignments. Oh, yes. Um, so you haven't taken the lockdown browser compliance test assignment, but you. Uh-huh. Right. Well, so I don't completely understand, but and I'll double check this, but the last time I checked a couple of days ago was set up correctly. Um, but if it's not, by the time we get to the exam, you'll definitely have to take the lockdown browser compliance test to be able to get access to the stage one. And because ICAF is in this module, it's supposed to also be locked down. And so if you can get into this module without taking the lockdown browser compliance test, then that's something weird on Canvas. But I'll double check that. But do take the lockdown browser compliance test because it is like 0.25% of your midterm score, and it will be by the time of the exam. I'll investigate this, but it at least says that you can't get into this module without taking that other module, and that module requires you to take that test there. Yeah. Oh, I see. Gotcha. So you can click, and that's fine. That makes sense. Well, in some ways, it doesn't make sense because I've had other issues where if I have things in locked modules, it like makes them unavailable. So that's a little weird to me, but it's not a problem. But so that's it. You won't. So the midterm, though, I think you will have to. I don't think I have links to the midterm any other place on Canvas. So you'll have to take the compliance test to get access to this module, to get access to the midterm, and that's where all the other these resources are as well. So there's like sample midterms and solution sets, other practice activities and so on. You'll need to take that compliance test to get access to that module. All right, yeah. Yeah. Yeah, I would say that Arena is sort of considered open notes. Yeah, absolutely. That definitely. More questions online. Will the difficulty in the practice exam match the actual difficulty in the actual exam? Well, I would say that the sample exams I've got from previous semesters definitely are going to be very similar. So each semester when I create an exam, I kind of go through the same process, and I use the previous semesters to I try to match things up. Like in this semester, I ask these types of questions. So in this semester, I'm going to ask something that's, I feel like it's kind of similar. So if you look at the sample exams from previous semesters, if they're associated with the previous semester, that definitely, I think, would be on par as a good model for what the exam is going to look like. Other practice resources I've put on there might push you a little bit farther just to sort of force you to kind of study a little bit more. But the sample exams definitely will be a good model. Any other questions? All right, so then, like I said, there's plenty of other resources too. The homework solution sets so far. There's the lecture slides. They've got book chapters associated with them. So if you're having trouble understanding the way I explain something, I recommend you say, for that lecture, it's associated with this chapter. Take a look at what the Banks book says about that, and so on. And then, of course, all of the lectures are recorded, not just for this semester, but for previous semesters. And there's other resources as well. So lots of resources available on Canvas that hopefully will be helpful. All right, so this is just explaining the timing of it. So they replace the normal lecture periods. You can take them here, as I was just saying. These are the resources that are sort of available. Oh, no need to copy grids of numbers from the back of the book. If you need statistical tables, like for t-tests and z-tests and chi-squared tests and ks tests. I'll provide you all of those statistical tables. You'll have to know how to use them, but you don't need to copy down, a bunch of grids of numbers. Yeah, so then there was format questions. So frequently I like, multiple bubble or multiple select questions. Don't be surprised by select all. Each question is 1 point, as I was talking about. The whole exam, both stages together, are 20% of your grade. Okay. I don't actually remember the average from last semester, but I think it was around, after all of the things were pulled together, both exams together, I think that the average was like an 80. So it wasn't too awful. It was not these like 40% things. So, and that I think is a target I wouldn't mind hitting. Okay, so the basic ingredients that go into me when I design these exams is I try to hit, if I was designing it on paper, this is sort of the ideal. And then I take my kind of paper-based solution and I break it up into sort of multiple select that I can implement on Canvas. And so I kind of am shooting for like 10 to 13 kind of conceptual questions about things like modeling, definitions, pick the name of a statistical test, calculations based on a, like I would say hand simulation, that's sort of what we're saying here. Statements about graphs, and like, so can you spot the PDF? Can you spot the CDF? And then things like number sequences. Does this number sequence violate independence, uniformity, those sorts of things? Then a few numerical problems, like can you do a hand simulation? Can you generate random numbers, a few of them? Can you do the sort of statistical test that we talked about, the KS test, the chi-squared test, and the runs test? Then design problems. Can you design a random variate generator? So this, like I said, might be broken up across 3 to 4 questions, where I might have you invert a simple PDF. I might, I'm sorry, integrate a simple PDF to CDF, invert a relatively simple CDF, and you might, I like the square root thing, that square root issue. So make sure you know how to choose the signs, and then generate numbers. So if I give you some random numbers, can you generate random variates using that inverse? Also, discrete. So, that homework that you just did was focused on continuous random variates, but if I give you a probability math function with 3 or 4 outcomes, can you, if I give you a bunch of random numbers, convert those random numbers into outcomes according to, and in the sort of inverse transform method for that discrete distribution. So, so that's something else that I have to make sure you sort of know how to do. So that's the basic layout for the exam. Moving forward here, I've got some homework feedback, and then after this homework feedback, then there's just kind of this review section here is just going to have kind of greatest hits from the lecture slides. Like if I go through all the lectures I've gone through so far, what do I think are the salient points for each unit, so that I can kind of like say, these are the things that if you're prioritizing your studying, I would hit these things first. So that's what I've got so far, but I can also let this be driven by your questions. And so are there any specific questions you want to make sure that I cover before we go into anything else? I see a question online. Why did the practice exam ask questions on book examples? We can't use the book in stage 1. So I think the practice exercise, when referring to the book, just to, again, as a study tool, but the sample exams, like where it says, fall 2020, midterm A, those are the ones that are a good model for the actual midterms. I've tried to give you study materials that I think will be useful in studying, but if you're actually looking for like, what does a midterm look like? Look at the sample midterms, like fall 2020, fall 2019. Those are the ones that are there, where I've provided you exams, blank exams, as well as solution sets. All right, so any other questions before we just kind of, oh yeah, sorry. The Kolmogorov-Smirnov, the KS test, yeah, I can do that. So, and in fact, I actually think I've got, so I can show you the canned example, but I can also try to cook one up. I guess I can just come up with some numbers here and try that. So let me flip, I'll stop this share and I'll share from the tablet here and just work things out. Notes. All right, so let me see if I can switch. All right. Okay, so hopefully this is relatively clear in person here. So, so this is a KS test example. And then I can distribute this PDF as well online if that's helpful. So as a review, so what does the KS test help us test for? Anybody? So I'll say it's a test of what? Anybody? So this came up in random number generation. There are two major things we have to test for in random number generation. So it should be one of these two things. Uniformity came up online. All right, so this is a test of uniformity. We will learn how to use it for testing for other distributions after the midterm, but for now it's just a test of uniformity. So I might give you a sequence of numbers. So I can give you a sequence of possibly uniform random numbers that we don't know were drawn from a good random number generator. So these will all be between 0 and 1. Because they're plausibly from a PRNG. And so let's say I gave you like 0.9, 0.25, 0.7, 0.4, 0.1, and just to make the math easy on me, I think 5 numbers is not so bad. So I could give you any number of numbers, but just to make the math easier on me, I'm just going to do 5 for here. So can anybody tell me what's the first thing we do in a Kolmogorov-Smirnov test? I give you a bunch of numbers. Organize, sort them, right? So first we sort. And so from decreasing to increasing, so I guess it'd be 0.25, 0.4, 0.7, 0.9. It's the exact same list, but sorted. And then the null hypothesis that they're uniformly distributed is going to mean that basically this one should be in the bottom 1/5 of the interval, and this one here should be in the top 1/5 of the interval, and everybody else should be in the the 2nd 5th, the 3rd 5th, and the 4th 5th. That's the null hypothesis there. So in order to test for that, we're going to effectively measure the distances from those. And so in my KS test table, I can write in the middle of the table my random numbers. And in the top of the table, I can sort of write the upper barrier of the bin that I expect that number to fall in. And so that's going to be whatever the number's index is divided by the total number of numbers. So here we've got an n is equal to 5. And so this, by the way, these numbers here, I'm going to index R1, R2, R3, R4, and R5. And so for this first one, we've got 1/5. which is equal to 0.2. And that first number is 0.1. And then down here, we've got I minus 1 over n. And so that's just going to be equal to 0 over 5, or 0. And I can do the same thing for all 5 numbers. So the upper boundary for the first bin is 0.2. For the second boundary is 0.4. Maybe I'll do it in a different color just to make the columns easier to see. So this is 0.25 is my second number, and 0.2. My third number, 0.6. My fourth is at 0.8. And my last one is at 1.0. All right, so for each one of these, the middle number is the actual random number, and these boundaries are the bins that the null hypothesis would predict that number would fall in. All right, so any questions about that so far? What that table means or how to set it up before we move to the calculation step here? Okay. All right, so then we need to do our deviations from these things. So basically my first row here is going to measure the difference from the top boundary. So this is I divided by n minus Ri. And so for each one of these, I can go down through and I can say, well, 0.2 minus 0.1, that gives me a 0.1, 0.4 minus 0.25. I hate doing math in public, but it's 0.15, I think. Correct me if I'm wrong. 0.2 for this one, 0.1 for this one, 0.1 for this one. And if I look at all of those, the max difference in all of those is 0.2. So then I can do the other half of it, Ri minus I minus 1 over n. And that gives me 0.1, 0.05, 0, 0.1, and 0.1. And when I look at that, the max for the bottom row looks like it's 0.1. So my D value here, so the KS statistic, so I'll call this the KS statistic, is going to be the bigger of these two, so it's 0.2. And this is for a degree of freedom of n is equal to 5. So I need to compare this to whatever the D star value, the critical value here, I'll call it D star, for an alpha, which if I don't say anything, it's going to be 0.05, will be the alpha, the significance level. I'll try to say it. So it'll be D of 0.05. So I don't know that off the top of my head, but I would then look at the table and I would find this value down here in the table. And then I would compare D to D star. And if it's greater than D star, then I would reject the null and say these are not uniformly distributed. If it's less than D star, then I would fail to reject the null. And I can't really say anything formally about it. I can say that we can't reject the possibility that these are uniformly distributed, but there's such a small number of samples that it might just be that I don't have enough samples to really make a strong claim. Though with a KS test, this is one of the ones where it's almost pretty safe to accept when you don't reject, but we'll get to that after the midterm. So for now, we just fail to reject. So I'll write that little summary up here where If D is greater than D star, you reject. If D is less than D star, you fail to reject. And that's your KS test. So any questions about that? Questions online? And I see in the poll everywhere, there's a comment that, well, so one, somebody says the stage 2 is not timed. Again, stage 2 is not timed. It's exactly the same as stage 1, but you're free to take as much time as you need in that availability window. Then there's a comment that stage 1 says it closes Wednesday at 7 p.m., not 11:59. I just checked this morning, and I'm pretty sure it said 11:59, but I will go, before stage 1 opens, I will go through and double check all the dates so that you definitely have the full 72 hours, Monday, Tuesday, and Wednesday for stage 1, and Thursday, Friday, and Saturday for stage 2. Okay, so no questions on that? Yeah. I mean, I could ask it different ways. I would say that if you're given this whole section here, this would be kind of in the bottom 2/3 of the exam, where I would expect you to spend a little bit more time on it. I might ask you for either the conclusion, or I might actually ask you for something like the statistic. So, so either way, it's going to be auto-graded. And so I could do a calculation question. There are ways to automate this so that on Canvas, I can randomize the numbers that everybody gets. And so everybody actually gets a different KS test, but they'll have the same number of numbers, and then have to go down through and do it. So that's something else that I could do. Okay, so while I've got the tablet out, are there any other numerical, burning questions that you'd want me to do an example of? If not, I'll flip back to the slides, but we can go back to here as needed. All right. Zoom. Okay, so just some quick, homework feedback, like, all the way back to, homework B1, the fundamentals. Make sure to know those. I mean, I definitely am going to ask you about like the difference between entities, attributes, activities, events, state variables, delays. These are all going to probably definitely come up early in this exam. Events are activities, events are instantaneous, activities are durations. That's a distinction that when we look through a lot of the answers we see on this homework, that sometimes becomes confusing at first. Hopefully by now, you're starting to see that events happen at an instant, like it's an arrival, and an activity is a duration, like the time between arrivals. So that's kind of what I'm saying here. FEL, the future event list. So the FEL has a bunch of events on it. It's also the schedule, event calendar, and so on. State variables and states. So, the state variable is the actual thing you use in your logic in Arena, whereas the states are the numerical values or the logical values or discrete values that are actually taken by the variable. That's another sort of, little distinction. An event is the thing that causes a state variable to jump from one state to another. So those are all just kind of, any questions about those terms? Let me bring the chat back up here so I don't miss anything. All right, yeah, and I missed, and I'm sorry, I missed the chat because I switched my Zoom, but yeah, thanks for answering that question about the first step in the KS test. Okay, question 2, the hand simulation of a DS. Be careful not to schedule events too soon. So, even though you can see that extra arrivals are coming, you only schedule the next arrival, not all of the arrivals all at once. A departure event is only scheduled at the instant you process the beginning of that service. So even if you can anticipate in your head that there's going to be a departure event, when you're doing the hand simulation, make sure you wait until the activity starts to schedule that new primary event of, say, the departure or the end of the service. So yeah, we've got this time ordering. Scheduling, so yeah, this is just sort of another conceptual thing about, we think about scheduling activities, and if you can sort of think of yourself as scheduling an activity as opposed to scheduling an event, it can maybe prevent you from accidentally scheduling too many events, because you kind of know that, like, I'm not allowed to schedule an event until I schedule my activity. So if the activity hasn't happened yet, the corresponding events haven't happened yet. So it's all I'm kind of staying there. So those are kind of the key takeaways from B1, the kind of terminology stuff here and the hand simulation things here. Everybody feel pretty comfortable with that? Any questions about hand simulation or the kind of DES fundamentals, the terms? Yeah. Oh, good question. So what about the lab activities? I'm not going to ask you things about like NetLogo or whatever. Lab activities that support these things, like hand simulation and these terms, are, I mean, those are meant to kind of go together. But if, especially pre-midterm, the only thing that, well, it's pretty much even pre-midterm I'm thinking about, I may ask arena questions, but the arena question I'm asking me extremely limited. And they'll probably be things like knowing the syntax of disk and cont, because those are things that we actually got into where if I need to actually simulate a probability mass function, I need disk in arena. So know disk and know the difference between disk and cont. But I'm not going to ask you like where to find replication parameters in the run setup or things like that. So those practical issues about how to use arena, we don't really get into those until the final exam. Yeah, that was the latest lecture, and I can also go over that sort of thing. But yeah, if you look at the latest lecture on random variate generation and go to the slide on how to generate discrete random variates, there's a slide in there about how to do it in arena, and it shows you that all disk does is sort of encode the inverse CDF in its arguments, and so it'll show you how to do that. All right, any other questions about at this point? Questions online? I'm just going to mark some of these here. It's done. Okay. I see a question online. So somebody asked, we should only have one arrival event and one departure event in each period, right? And I would say for a single channel, single server queue, you will always have, so long as there's inter-arrival times left in the list, and there always should be, you'll always have one arrival in the FEL. You may not have a departure, but you'll never have two departures. So you'll have at most one departure, always one arrival in the FEL for a single channel, single server queue. If I had multiple servers, that's a different question. So if it's like an MM2 where it's a single channel, but there's two servers, then I might actually have two departures because both servers could be busy. And so both of them have got a corresponding event for when someone's going to clear out of that server. So yeah, be careful about the rules. For the homework, I gave you those tips because you were simulating that single channel, single server queue. But for a generic system, you can have more arrivals and more departures. It just kind of depends on what processes you're simulating. Hopefully that makes sense. But so if I ask you something like that, I might actually say, you know, assume you have a single channel, single server queue. How many arrivals would you expect to have? I could ask a question like that. All right, so the second homework, random number generation. So you used so random numbers, uniformity independence. You did the linear congruential generator. So for the LCG, the random number is the thing that's between 0 and 1. So if I ask you to generate a random number, I'm looking for a number between 0 and 1. So the internal state variables inside the PRNG those might not be between 0 and 1. They're going to be smaller than the modulus, but they could be 1,004 if the modulus was 10,000 or whatever. Those are not the random numbers. The random numbers is a term we use for uniformly distributed between 0 and 1. So that's the thing divided here. And likewise, and I mentioned this a couple of times, if I give you a random number seed on the midterm, your first number is not the seed divided by the modulus. You have to run the seed through the expression. And the first number you get out of the expression, that is your x1 divided by the modulus, and that's your first random number, r1. So there is no r0. There's no random number that corresponds to the seed. Hopefully that makes sense. Any questions about that? Okay. Yeah, this is all I was saying here. The seed should not be used to generate a random number. This is surprising, but place value is actually easy. It even trips people up on the homework. So it definitely could trip you up in the midterm if you're going kind of quickly here. So, be careful, like across these sort of tests here that, 0.18 is not greater than 0.127, or sorry, 0.127 is not greater than 0.18. This happens, a lot in the homework. Like people are just working quickly, and they see 127 and 18. So of course, this is the right thing here. Similarly here, and then this happens a lot. That dropping the zeros. So if you get a state variable inside the PRNG is 71 and the modulus is 1,000, make sure your random number is 0.071, not 0.71. I'm not going to throw in a lot of distractors that are going to see if you understand place value and sort of assuming that you kind of understand the rationale here. And if there are any errors, it's like, speed issues. But if I have you do a calculation problem where Canvas generates the numbers and it's looking for something within certain ranges, then in those cases, like, you might get marked off if you somewhere in the process, do one of these miscalculations, like 71 divided by 1,000, marking that as 0.71. So just be careful about place value. It's an easy thing to kind of mess up. The other things, degrees of freedom. So in this case here, for the Kolmogorov-Smirnov test, the degrees of freedom are the number of samples. For a chi-squared test, it's one less than the number of bins. For both the chi-squared test and the Kolmogorov-Smirnov test, you look up the level of significance is going to map in the table to what I tell you. It's only with a z-test that you have to divide that thing by 2, because in a z-score can be positive and negative, and that's why you have to worry about the 2-tail, 1-tail thing. But chi-squared values and Kolmogorov-Smirnov values can only be positive, so there's none of this 2-tail, 1-tail business. So if I tell you 0.05, you look in the 0.05 column, and for a KS test, it's the number of samples. For a chi-squared test, it's one less than the number of bins. So questions about that? Okay, other things for question number 2. So, make sure that if I ask you to pick out some sort of interpretation, make sure you kind of know what the test is saying. So in both the Kolmogorov-Smirnov test and the chi-squared test, the null hypothesis is uniformity. And so we are assuming uniformity to get the math out. We can't assume non-uniformity because I don't know what non-uniformity is. That's like a million different things. So we assume uniformity. That's what makes the test go. And then if we get a huge deviation, we're measuring a deviation from uniformity. So the null hypothesis of uniformity, if you get a large number for chi-squared or for KS, then you are far from uniformity. And so if you reject the null, you are saying that it is very unlikely that these numbers came from a uniform distribution distributed between 0 and 1. So that's kind of what I'm sort of summarizing here. So if I were to ask a question like, is this a good pseudo-random number generator? So I might say that here's a bunch of numbers, use a chi-squared test to evaluate that this is a good pseudo-random number generator. If the chi-squared test or the KS test rejects uniformity, then the answer here is no. And if I look for reasoning, I've got no comma and then have a bunch of different reasoning, then you could say no, because the chi-square test or the Kolmogorov-Smirnov test rejects the null hypothesis of uniformity at the significance level of 0.05 or something like that. All right, so any questions about how to interpret these things? What we mean by null hypotheses and how null hypotheses being uniform and so on. So sometimes it feels good to get a low p-value or to reject the null, but you know that it's good in that you detected a deviation from the expectation, and it's always good to have a detection. But that deviation indicates that the random number generator is bad. Okay. All right, and then the last homework. So this is the freshest, and so you know, just kind of step through this example here. This is the one that I think it's still available for you to turn in up through Saturday night, and then the solution set will go available Sunday. And so this isn't the problem that's on the homework. This is just another example that I've put together here, but it's very similar to the one that's on the homework. And the biggest thing here is that when you're integrating the density function to the CDF, don't just take antiderivatives of all the pieces. So a lot of people will look at this density function and they'll say, I'm going to just take the integral of 0. That's 0. I'm going to take the antiderivative of 0.25, that's 0.25x, 1.5, that's 1.5x, and 0, 0, and that's my CDF. But that's clearly not a CDF because, for one, it doesn't end at 1, and we know all CDFs should end at 1. So that should be a red flag we did something wrong. So that's not how we do it. So it's more complicated in that we have to break the thing up across the units of the limits of integration. So we don't know how to take an integral of a piecewise function here. So we have to effectively take integrals of each piece and add all the pieces up together. And that's how we generate the integral. So the integral from negative infinity to x is, well, it depends on where your x is. And so if your x is between 1.5 and 2 in this example, then you need to do the integral from this bottom piece, the integral of this middle piece through its whole range, and then finally the integral of this through its kind of partial range here. And that's what I'm kind of stepping through here. So, this first part is just the integral of this thing up through negative infinity. The second part is that whole thing and its whole range, plus the partial range of this one, which is what I've done there. And also make sure it's not just antiderivatives. Like, you want to make sure that you're actually doing the full limits of integration. So if you look at this integral, it goes from 0.5 up to x. So you need to take the antiderivative and then evaluate it at x and also evaluate it at 0.5. And so that's what we're doing here. This is the antiderivative evaluated at x. This is the antiderivative evaluated at 0.5. And I simplify that whole thing to get that part of the CDF, and so on and so on. So I end up getting a CDF here that starts at 1 or starts at 0 and ends at 1 and is non-decreasing throughout the whole range. So any questions on that, on integrating these piecewise PDFs? Questions online? Okay. All right, so definitely know how to do that. You'll definitely be asked about, I think that on the midterm. So then the inverting intervals, another important thing. If I give you a CDF, I might ask you to generate the random variate generator by taking its inverse. And so if I want to invert this thing, I have to deal with all these pieces as well. And then I also potentially have to choose signs, like if I have ambiguity because something is not a one-to-one function, like an x squared is not a one-to-one function because there's, for every x, so we could say there's 2 y values that, I can say for one y value, it can get 2 x values, and that's what makes it non-invertible. So x squared is not invertible, and so if I get an x squared and I want to invert it, I have to choose which side of x squared to pick, and that's like choosing the signs and that taking the roots. So I have to remember that the CDF the inverse CDF is going to map 0, 1 to the full range. The range are only the parts of the CDF that vary with X. And so this is not actually part of the range. So if you think about it, if you take the derivative with respect to X of this thing, any pieces that are 0 are going to be in the parts of the density. We're going to set, they'll have density equal to 0. And density equal to 0 is not in the range. So the only thing that's in the range here are these middle 2 parts. So those are the only things that I'm going to have to worry about inverting. So I just have to, so that's what I'm saying here, figure out what range of R corresponds to this range of X. And likewise for this, what range of R corresponds to this range of X, and then invert those little pieces. So that's what I've done here, is I've said, all right, these are the only ones I care about because this goes through my range from 0.5 to 2. And I can then figure out from there, from 0.5 to 1.5, well, that corresponds to an R from 0 to 0.25. So if I plug in 0.5 into this thing, I think I get a 0. If I plug in 1.5 into this thing, I think I get a 0.25. And so this range here corresponds to this R range here. So I now can set R equal to this thing, solve for X, and that is my inverse generator just for this piece here from 0 to 0.25. And then I do the same thing for this second piece. So before I go on and show that, are there any questions about this part, like this half, just doing the inverse for this top piece? Okay. All right, so then the bottom piece here, so I can see that from 1.5 to 2, if I plug it in there, I get a range that goes from 0.25 to 1. So that's good. So I am now going to set R equal to this. That's what I've done here, R equal to this bottom piece, solve for X, and there's my inverse transform generator for this range here, and that fills in that box there. So that completes that inverse transform generator. And so as a safety check, I can make sure that if I plug in an R value into this, and then take that value and plug it into the CDF, I get the R value back, and vice versa. If I plug in an X value into here, I'll get an R value out. If I plug into here, I should get the same X value back. So that's my safety check. And I can check boundary conditions. So I can check that 0 gives me 0.5. I can check that 0.25 gives me 1.5, and so on. All right. So, so that's a simple inverse. And then the only other question I want to go over here is this non-invertible function business, primarily squares. So any questions about the general inverse problem before I point out how to choose the signs? Usually questions about how do we go from these ranges to these ranges, etc. Where we feel comfortable. Questions online. Okay. All right, so then the last tricky thing for this homework is what if the CDF is not invertible? And on a midterm, I'm probably only going to bother you with squares, but this could apply to other non-invertible functions too. And so the simple example of this is what if my CDF is described by this quadratic, x plus 1 squared over this range, -1x to 0. Well, I can plot all of x plus 1 squared, and it would be this bowl here, that it goes from -2 to 0, and it's this bowl shape here. But I know that CDFs are only non-decreasing. So I see the range here starts at -1. So this black portion here isn't in the CDF, it's only this blue portion. So the CDF itself is invertible, but technically this functional form here, x plus 1 squared, is not invertible. So when I invert it, I need to make sure that I'm inverting the right-hand side, or the part that's in the CDF, and not the left-hand side that's in the black portion. Because if I invert the wrong portion, then I'm going to generate numbers outside the range. The range here starts at -1, and this black portion corresponds to numbers less than -1. So I don't want that. So I can set R equal to this thing. I go down through it here, and after I try to solve for X, So I get x plus 1 is equal to square root of r or negative square root of r, which is equivalent to saying x is equal to negative 1 plus square root of r, or x is equal to negative 1 minus square root of r. Now I need to figure out whether I want a plus or a minus. Does anybody have a guess? What's the right sign, plus or a minus here? In class, what was that? Did I hear a plus? Or, how many people say plus? How many people say minus? All right, so I think I see more minuses, but kind of timid on both sides. All right, so if I look at this, I see that the range starts at -1 and climbs to 0. So my range needs to go from -1 to 0. Well, if I look at this x, it is going to be, the square root is always going to be positive. The magnitude of the square root is positive. So the question is, like, am I going to want my range to go from -1 forward or -1 backward? Because if r is equal to 0, x will be -1. If r is equal to 1, x will be equal to 0. Here, if r is equal to 0, x will be -1. But if r is equal to 1, x will equal to -2. So that tells me that plus is the right solution here, because this one is going to actually, for r values from 0 to 1, this will give me x values from -1 to 0 that are in the range. So that's why I would choose the plus value. So questions about that? Questions online? Okay. And that's just what I'm showing here. We want to make sure we're on this side of the curve. Okay, so that's all my feedback from the homeworks. Happy to take questions about that. We have about 15 minutes left. So I'm also happy to march through, like I said, these next slides here are just me pulling out things that I think are important from each unit. But these are all things you've seen before. So they're meant to sort of motivate questions from you. So, so any other questions that I should definitely cover while you've got me here? Questions online? All right. So going way back to the beginning here, the fundamentals here. What is a model? And we remember how did I define a model? Models answer what question? What if? Remember that. That's like my big thing. Like everybody, other faculty know that I'm the what if guy. Like that's how I define models. And so it's not surprising if I ask you a midterm question related to how you define models. So models are defined by what they're used for, not what they're made of. Models are made out of people, like Soylent Green. Models are made out of animals. Models are made out of math. Models are made out of computers. Models are made, again, out of math. It's not what they're made of that makes them models, it's how they're used. And anything can be used to answer a what if question. So anything could be a model, depending on how it's used. All models are wrong, but some are useful. So our question is not, how do we make the model the most accurate, the most realistic, the most detailed? The question is, how do we squeeze the most insight out of the model? So that's another kind of an important thing. It's not about adding detail. It's about maximizing the illumination and utility of the model. And sometimes that actually happens by reducing detail in the model. So there are static and dynamic models, stochastic and deterministic models. Know about the relationship between stochastic modeling and randomness. So I've seen this come up in questions I've gotten about the labs already, is that you'll say that the randomness that you're putting into your first arena models are not actually reflecting randomness in the real world. Like in a two-way by condition versus a two-way by chance, the side block, the name two-way by condition sounds like what's going on in the real world. Like if you're saying this part is going through, I'm going to check its condition to see if it fails a test or not. But I don't want to add all of those conditional details into my model. And so I just look at the stats and I say the quality control folks tell me that the process that they use has a 75%, or maybe has a 25% failure rate. So I trust my QC engineers to say that 25% of the parts that come out of here are going to fail and the other 75% aren't. Hopefully it's better than that, but but I trust the numbers that come from them. So when I sim, I don't need to know all of the minute details about how the part works. I just need to know that fraction, the statistics. So stochastic modeling is using statistics in place of those details. So, know that sort of thing. And stochastic comes from the Greek for conjecture or guess. We're taking a conjecture that the system is random, even though it's actually not. So, why do we use experimental models? What are strengths and weaknesses of different types of models, from smaller, microscale models all the way up to, or from microscale models being the most complex, to very macro scale models like system dynamics modeling, different uses for modeling. These are sort of very high level things. I'm not going to ask you a lot of questions on these things, but I'm definitely going to hit these maybe 2 or 3 times. Components of a simulation model, those are far more important for this class. So definitely expect to be, asked about those things. So do you know the differences between all of these things? Do you know all of the components of a DES model? These terms down here. Can you walk through a hand simulation model? If I were to give you this table, but leave out a couple of different spots, could you fill them in? Those are the types of things that I might ask here. And by the way, stepping through this hand simulation model, we haven't talked about it in lab yet, but there is this little step that's, there's play over here and fast forward over here, which turns off the visualization. You can hit the little step button, and that actually does the same thing you did in your hand simulation, where it goes from event to event to event, and you can actually debug your model and watch it step from scheduled event to scheduled event. And that's, what we did there. So, make sure you know the hand simulation table, make sure you can tell the difference between activities, different types of activities, and delays. So kind of important there. So activities are unconditional weights, delays are conditional weights. So again, the fundamentals. Any questions about the fundamentals there? Questions online? All right. So then, going into probability, that was sort of the next big topic there. So we talked about input models. So know what an input model is and the input modeling process, like this idea of choosing probabilistic distributions in order to model complex outcomes or complex phenomena in the real world. That is input modeling. Know the difference between PMF, PDF, and CDF. Expected value variance and standard deviation, common distributions. I think I'll list a couple here in a couple slides, but be able to, the ones that I highlighted, and I think I'll highlight them again in a couple slides. Those ones like normal distribution, exponential distribution, know their parameters, know a sentence description of when they're used, common uses, those sorts of things. Try to picture their PDFs at least, so that if you can see a PDF that's bell-shaped, you'll know that that's probably not an exponential. Know that if you want to make an exponential process kind of bump up a little bit, you can stretch it out with a Weibull, those sorts of things. So relationships between random variables and general parameters of random variables. And so again, this is my definition of input modeling. These are the ones that I kind of hope you care about or know about. So continuous, uniform triangular normal, the exponential family, exponential, Erlang, Weibull, and Poisson. Know that Poisson is discrete and how it relates to the exponential. And then the kind of Bernoulli-based ones, Bernoulli binomial, negative binomial, and the geometric, which is just a special case of the negative binomial. Know that a Poisson counting process is a collection of Poisson random variables whose relationships make interarrivals exponentially distributed. So that's kind of an important thing there. So those are key concepts. And if you need a refresher, here's kind of my, those continuous variables. Here's kind of all their parameters. Here's a basic description of what they do. Here's those discrete variables that I care about. Here's their parameters. Here's what they do. So any questions about probability? Questions online? Okay. So then that brings us to generation, the design sort of problems. So know the basic, like what are the, how do seeds work? What are the required properties, independence and uniformity, maybe some of the desired properties, they're fast, they're reproducible, definitely know the LCG. I won't give you the LCG formula. I might tell you a multiplier, a modulus, and an increment, and then a seed, and then ask you to generate them. So make sure you know how to take those 4 pieces of information and generate random numbers. Know your chi-squared and Kolmogorov-Smirnov test. I'll give you the tables, but you got to know how to do the test. Test for independence. Know the term autocorrelation. Be able to do a runs above and below the mean. Random variate generation. Basic understanding of how a random variate generator expressions can, in theory, be used in ARENA or in Excel. Know how to do an inverse transform method, as we have talked about already, not only for continuous, but also for discrete. And know, some of these comments, the last sort of things we talked about here is how in ARENA, there's this disk that encodes the inverse CDF and the cont, which kind of interpolates between it. Know the sort of the syntax, definitely of disk here and how that works. So I've just got a couple of slides on those things. The basic idea here with PRNGs, you put in a seed and it very quickly should be able to generate a sequence that has a very long cycle, but given the same seed, it'll give you the same sequence all over again. If I give us different seeds, then they'll give us different cycles that are independent from each other, and that's how we generate independent replications in a computer. Again, LCG, test for uniformity, chi-squared and KS. Know that autocorrelation characterizes correlations in a sequence with itself a little bit later. But the runs test is the big one that I need you to know, the runs above and below the mean test. And so I've got, example of the runs test here that I'm not going to step through, but unless you'd like me to, but, be able to work. Oh, this is the chi-squared test. This is my KS test. These are a couple extra notes about autocorrelation, but I'm not going to ask you anything in this detail. I'm just providing a little extra info about autocorrelation. And then finally, the runs test. And so examples there of the runs test. So any questions about those tests, those properties, uniformity, independence, be able to spot non-uniform numbers, be able to spot independent numbers. I will make it egregious. If I give you a sequence of 20 numbers, they will be really non-uniform or really not independent. It will be very clear. So, and it could be both. So, yeah, like it could be 1, 2, 1, 2, 1, 2, 1, 2, 1, 2 as both non-uniform and not independent. Inverse transform stuff. So again, be able to go from PDF to CDF, be able to invert the CDF, be able to generate a variant. This is basically graphically what that looks like. There are, you don't need to know this table. If this table comes up, I will give it to you. I'm just bringing it up here just to point out that there's this other term, inverse CDF, also goes by the term quantile function. They're synonyms. So know that term, quantile function, because very often when you do random variate generation in the real world, you often just have to Google for what the heck is the inverse CDF for this distribution. And sometimes that doesn't work. And then you say, well, what is the quantile function for this distribution? And it comes up. So I want you to know both of those terms. Yeah. Say it again, if you. I would say that, I mean, I might, it's possible that I could ask you to integrate something that has an exponential in it. I won't ask you to generate the CDF for an exponential, but I might ask you to integrate something that's exponential-like. And so maybe having these things would, help you sort of remember those things, but I don't know how useful it would necessarily be to have these things. I mean, maybe triangular would be a good one to sort of keep in mind because it kind of demonstrates a lot of properties all at once. Oh, you can use, no, I didn't mention it, but if you would like to bring a calculator, that's fine. I am trusting you to not load any screenshots of other things on it, or use it for communication, wirelessly or otherwise. But yeah, I don't think you'll need heavy calculus use of the calculator. A simple business calculator would probably be fine, but I'm not putting any limitations on calculator use. All right, we just got like a minute left. The only other things that I'll just want to show up here. Here is the disk. This is the disk syntax. So it's just the inverse CDF. So it's basically you take the CDF, but you put the CDF function first, and cont is just the interpolation of that thing. Disk is sort of the most important one to kind of know. And I think that's pretty much it. The only other things I have here are like, can you recognize PDFs and CDFs? And that's it really. So anything else anybody has before we run off and you've got the weekend to think about stage one? Questions online? If not, I'll just give everybody attendance credit for today, so don't worry about that. And see you or not next week. And so some of you I might not see for 2 weeks. So it's all on Canvas. Feel free to come here. You don't have to. Uh-huh. Well, just give me 1 second since it's about the lab here. Let me at least disconnect the recording. And any other questions online? If not, I'm going to start wrapping up here. All right, great. And then I will end the call here.